Hello and welcome to Physics with Amol sir. So this video is for class 12 and we are going to continue with the chapter of current electricity. So in the last class we spoke about Kirchhoff's rules. Okay, so these are very important rules whenever we are studying about current electricity. So make sure that you have understood those rules very properly. Today we are going to see the application of these rules. Okay, we will see a concept called as the meter bridge. Okay, or the Wheatstones Bridge. And using the Wheatstones Bridge, we are going to see how we can use that Wheatstones Bridge to find out any unknown resistance. Okay, so from the exam point of view, this is a very important topic because even a theory question could be asked or a numerical can be asked. Okay, so let's begin. So let us start with the Wheatstones Bridge. This arrangement that you see over here, this is called as the Wheatstones Bridge. So it might be confusing. Let us understand what it is. First thing you will notice, there are four resistors, R1, R2, R3 and R4. Okay, and you can see how they are connected. You will see that R2 and R4 they are connected in series with each other. R1 and R3 they are connected in series with each other. And then they are in together, R2 plus R4 is connected in parallel with R1 plus R3. Okay. Then you will see there is a galvanometer be connected between the points B and D. Okay, and of course they are connected to a power supply. Now, what is the purpose of making this? The purpose of having a Wheatstones bridge is to find out an unknown resistance. Let us imagine this R4. This is an unknown resistance. We don't know the value of this resistance. To find out this value, we are able to use the Wheatstones network. Right? R1 and R2, these are fixed resistors. We know the value of R1 and R2. R3 is a variable resistor. Variable means we can change the resistance. Okay, so this R3 is a variable resistance. Then these are the points A, B, C and D. You will see that the galvanometer is properly connected between B and D only. Okay, I hope you remember galvanometers. In 10th standard we had studied about galvanometers for the first time. See what galvanometers do, they are able to detect current in the circuit. So if there is any current flowing between 2 points, if you connect a galvanometer there, it will show deflection. So a deflection is shown, that means there is a current flowing. If no deflection is shown, that means there is no current in the circuit. Okay, that is why we are putting the galvanometer here. Okay, we will shortly see what is the full purpose of this. And then we have connected it to a power supply. For this particular purpose, it doesn't matter how much power supply you have attached, okay, because in our derivation that is going to be immaterial. Okay, there is a current I that is flowing through the circuit. Total current that is flowing is I. Okay, and as I said, the task of the Wheatstones network is to find out unknown resistance R4. Okay. Okay, having understood the entire connection, now let us go to our derivation. Now all these steps I have already written in the notes that I have provided to you. Okay, this full answer for the Wheatstones network you will find there. Okay, now let us begin with our derivation. So before doing any kind of connection, before doing any kind of reading, what we do is we check for our galvanometer. Okay, now galvanometer will show a deflection if there is current flowing in the circuit, correct? So if the point B and D, if there is any potential difference between them, what will happen is the galvanometer will show a deflection either to the right side or to the left side. The first task in the Wheatstones bridge, Wheatstones network, is to bring the galvanometer to zero deflection. How will you bring it to zero deflection? To bring galvanometer to zero deflection, the point B and D should be at the same potential. Is that correct? If B and D is having same potential, in that case galvanometer will show zero deflection. For that we adjust the value of R3. Okay, our variable resistor. We can either increase the resistance or decrease the resistance. If we adjust R3, you will notice at one point the galvanometer will begin to show zero deflection. Okay, so once the zero deflection has been obtained, then our work will start. Okay, so the first step in Wheatstones bridge in finding out the balancing condition is to first bring the galvanometer to zero deflection. To bring it to zero deflection, adjust the unknown resistor. Okay, once that is done, now let us begin. So as we said, I is the total current in the circuit. Now we have adjusted the galvanometer such that it is showing zero deflection. So there is no current going from B to D. Okay, there is no electric current going from B to D or D to B. The Ig, that is current through galvanometer, is zero. Now the current I comes over here. Okay, what will happen is it will get split into two parts. Okay, by the junction rule. Correct? Because whatever is the current reaching the junction, same will be the current leaving the junction. So what will happen is this current I, this gets divided into two parts. Let the current that is going through R1, we will call that as I1, and current that is going through R2, we will call as I2. Is that clear? So this current I, it gets split into I1 and I2. I1 reaches D. Okay, and because R1 and R3 are connected in series, the current through R3 is also I1. Is that correct? Similarly, let us go here. Current I2 goes through R2, reaches the point B. Point from B to it goes through R4. How much current will go through R4? 1 second. The current will be I2. Okay, so this is very important to understand. From R1 and R3, the current is I1. From R2 and R4, the current is I2. Then of course the current will reach here and again it will become I. Okay, so this is these are the currents that are flowing through these our resistors. Now we will apply the Kirchhoff's loop rule for two loops. One loop we will take is A, B, D, A. The other loop we will take is C, B, D, C. Okay, so let us begin. So first step, for loop A, B, D, A. Okay, we are going to apply Kirchhoff's loop rule for A, B, D, A. When you apply it for A, B, D, A, okay, let us go one by one. How much is potential drop from A to B? Current is I2 and the resistance is R2. We are going with the current. Because we are going with the current, the potential drop will be negative. So what I will get it as minus I2 R2 over here. Then from B to D, how much is the potential drop? Potential drop is 0 because they are at the same potential. So plus 0. Then from D to A, how much is the potential drop? Okay, it will be I1 R1. Correct? And we are going against the current. You can see the direction of current is A to D. Because we are going against the current, potential drop will be positive. So here I will write plus I1 R1. And this will be equal to 0 according to the Kirchhoff's loop rule. Now I can rearrange this and I can write therefore I1 R1 is equal to I2 R2, and therefore we can write I1 upon I2 is equal to R2 upon R1 and call this as equation number 1. Now please note these steps down as I am going to erase them. Okay, what you get, I1 R1 is equal to I2 R2, and therefore if you rearrange, we get I1 upon I2 is equal to R2 upon R1. That is our equation number 1. I hope you have noted equation number 1. Now let us go to the second loop, that is for loop CBDC. Okay, so we will go to CBDC. Here again we will apply the Kirchhoff's loop rule. So from C to B, we are going against the current, potential drop positive. So I will write it as I2 R4, B to D 0. Then from D to C, we are going with the current, so it will be negative. So minus I1 R3. This will be equal to 0. Okay, once again we will rearrange and we will get I1 R3 is equal to I2 R4, and therefore you can write I1 by I2 is equal to R4 by R3. This is equation number 2. So for the second loop you will get I1 R3 is equal to I2 R4, and therefore I1 upon I2 is equal to R4 upon R3. That is equation number 2. Once again note this term. Now if you compare equations 1 and 2, you will see the LHS is the same, that is I1 by I2. So we can equate the RHS. So comparing equations 1 and 2, we can write R2 upon R1 is equal to R4 upon R3. Correct? This is the equation we can get if we compare equations 1 and 2. And from here, very easily you can find out the unknown resistance R4. So therefore you can write unknown resistance R4 will be equal to R2 R3 upon R1. Okay. So this is how Wheatstones bridge can be used. This formula that you got, R2 by R1 equal to R4 by R3. This is called as the balancing condition of the Wheatstones network. In exam, you will definitely be asked this question. Find out or derive the balancing condition. You should find out this answer. Okay, and you should be able to visualize it by looking at the diagram also. How do you understand? See, left hand side, R2 by R1, R2 by R1. This will be equal to R4 by R3, R4 by R3. Getting the idea? So even if it is rearranged, does not really matter. You can find out the unknown resistance in this manner. Okay. So this is the balancing condition, R2 by R1 equals R4 by R3, and using this you can find out the unknown resistance. Any kind of unknown resistance can be found out using the Wheatstones bridge. Now we will see an application of the Wheatstones bridge. Okay, Wheatstones bridge we use in something called as a meter bridge. Here is a diagram of a meter bridge. So what is a meter bridge? Basically it is a wooden plank where we have a wire, right? And then we see an arrangement like this. Okay, so there are these metal strips are there, L-shaped metal strip is there inside, in the middle there is another metal strip. In the left gap we can put a resistor, in the right gap we can put a resistor, and as I said we have a 100 centimeter long meter wire. Okay, so it is 1 meter wire, therefore it is called as a meter bridge. The wire we put over here, it is having a uniform cross section. Okay, so it is a same kind of wire, correct? And then of course we can attach a power supply and a key to it. Okay, so this is the setup of a meter bridge. Task of a meter bridge is again to find out an unknown resistance. This is used in our laboratory as well. Okay, very soon we are going to see an experiment also based on it. So this is a meter bridge. Now how we can use the Wheatstones network, the Wheatstones balancing condition in the meter bridge. So in the left gap we have put an unknown resistance, that is R. In the right gap we have put a known resistance and we are calling it as S. Okay, that is S standing for the standard resistance. And this is the wire. Let us call our wire AB. Okay, it is a little easy for us to understand. So AB is our wire. Okay, 100 centimeter long wire. Now this wire has got a uniform cross section. Because it has got a uniform cross section, okay, we can actually write the resistance of that wire in terms of its length, right? So we are going to use a symbol RCM. RCM will stand for resistance per unit centimeter of this wire. Okay, so what is RCM? It is resistance per unit centimeter. So if you choose a wire of this much length, okay, a wire having length L. So wire having length L will have a resistance of RCM multiplied by L. Resistance per unit centimeter multiplied by the length in centimeter. Getting the idea? So this is the symbol we are going to use. Once again, this entire answer you will find in the notes. Now let us see the explanation. So what we have R in the left gap, S in the right gap, and this is our meter long wire. We have connected a galvanometer in the center. This galvanometer is connected to a jockey. Jockey means again it is another point that can be moved very easily. Fine, that is the task. Now what we can do, we can move this jockey along the length from A to B. Definitely there will be one point on this wire where the potential difference between these 2 points is going to be 0 and the galvanometer will show 0 deflection. Okay, that is the balancing condition basically. So we are going to find the 0 point for null deflection, and when we find that point, then we will do our explanation. Okay, so now let us see we are moving the jockey on this line from A to B. We find a certain point where the galvanometer is showing the null deflection, that is 0 deflection. Let that length be equal to L1, right? So from A to this point wherever we found the null deflection, the length is L1. Definitely, let us call this point wherever we found the null deflection, let us call it as C. So from A to C it is L1. So definitely from C to B the length is going to be 100 minus L1. Is that correct? Now let us use the balancing condition. What the balancing condition will tell us? Balancing condition will tell us at the null deflection, R divided by what is the resistance of L1 will be equal to S upon what is the resistance of 100 minus L1. Is that correct? That is the balancing condition of Wheatstones Bridge. So what you can write? We can write using the balancing condition for Wheatstones network, capital R upon RCM L1. You will notice we have used the symbol RCM. RCM, as I said, is the resistance per unit length, is equal to S upon RCM into 100 minus L1. Therefore, we can write R upon S is equal to, you will notice this RCM can get cancelled and R by S will be equal to L1 upon 100 minus L1. And therefore, you can find out the unknown resistance R. So, R will be equal to L1 into S upon 100 minus L1. So, all you have to do is find out this balancing length L1, and using that you can find the unknown resistance using the meter bridge. Okay, so that is an application of the Wheatstones Bridge. Now remember, if you want very zero error, if you want very less amount of error, we have to adjust L1 such that L1 will be in the center, that is close to 50 centimeters. To bring L1 to 50, this S has to be adjusted. S should be very much near to the original value of R. Okay, but that is something that we can adjust. We can have various kind of values of S, and changing S we can actually find out how much will be the balancing length, and we want to make sure balancing length will be very much near the center. So in the calculation the error will be very less. Okay, so I hope both these derivations were understood. From exam point of view, Wheatstones Bridge as well as meter bridge, they are important because either we can have numericals based on them or also the theory questions can be asked. So please make sure that you have understood both of them. All these answers, as I said, already you have in your notebooks. Okay. Now you are going to solve the solved numericals based on this. So after Wheatstones network, there is one solved example, and after meter bridge, there is another solved example. Make sure that you go through them properly. Okay, and make sure that you are understanding. They are very easy. All you have to do is apply the formula. You will get the answer. But make sure that you understand properly. If again there are any doubts, make sure you are asking. Okay, thank you.